A new generation of commercial nuclear power is currently moving from laboratory design to physical construction. These are small modular reactors, or SMRs, highly compact, factory-built reactor modules designed to be deployed across decentralized grids. But this entire deployment schedule is currently paralyzed by a severe bottleneck in the fuel supply chain. The legacy light water reactors operating today run on low-enriched uranium, or LEU, which is uranium that has been enriched to contain roughly 3 to 5% of the fissile isotope U-235. Advanced SMRs cannot run on this fuel. Their designs strictly require high-assay low-enriched uranium, known as HALEU. HALEU must be enriched up to 19.75% U-235, resting just below the 20% boundary that defines weapons-grade highly enriched uranium. This chart shows projected annual U.S. demand for HALEU versus current domestic production. The demand curve surges past 500 metric tons annually by 2050 to support decarbonization scenarios, but the domestic production baseline sits near zero. Historically, the United States allowed its enrichment infrastructure to atrophy, leaving Russia's state-owned Rosatom as the only entity on Earth possessing the commercial infrastructure to manufacture and export HALEU at scale. Following recent federal bans on Russian uranium imports, the U.S. and allied nations are now forced to synthesize an entirely new domestic supply chain. Breaking this foreign monopoly requires scaling up one of the most mechanically demanding applied physics processes ever engineered. To understand why this fuel requires such extreme processing, we have to look at the atomic architecture of uranium. Natural uranium consists of two primary isotopes, U-235 and U-238. U-235 fissions, while U-238 does not. The difference comes down to quantum mechanics, specifically nucleon pairing energy. This diagram illustrates why U-235 is fissile. It contains 92 protons and 143 neutrons, an even-odd structure. When it absorbs an incoming slow-moving thermal neutron, it briefly transmutes into a highly unstable U-236 compound nucleus. This absorption releases pairing energy, yielding over 6.5 mega-electron volts. That is more than enough excitation energy to breach the 6 MeV fission barrier, causing the atom to split and sustain a chain reaction. U-238 behaves entirely differently. It already has an even number of protons and neutrons. When it absorbs a thermal neutron to become U-239, it transitions to a less stable state, missing out on that crucial pairing energy release. The reaction yields only about 4.8 MeV. Falling short of the fission barrier, the U-238 nucleus simply absorbs the neutron, emits a gamma rate to stabilize, and transmutes into a heavier element. It is fertile, not fissile.
Because U-238 makes up 99.27% of natural uranium and cannot sustain a thermal chain reaction, engineers have exactly one option to generate commercial nuclear power. They must artificially isolate and concentrate the rare U-235 isotope. This physical requirement scales geometrically. Traditional light water reactors are massive structures. Their sheer volume ensures that most neutrons born from a fission event will eventually hit a U-235 atom before they can reach the edge of the reactor core. Advanced SMRs shrink this footprint almost entirely. This compactness introduces a problem known as neutron leakage. As the physical radius of a reactor core shrinks, its surface-to-volume ratio increases. A higher percentage of neutrons simply fly out of the core boundary and escape before they ever strike a fissile target. Many SMR designs operate on a fast neutron spectrum, meaning they abandon the water moderators used in legacy reactors to slow neutrons down. Without water, these fast neutrons travel at high velocities, significantly lowering their probability of colliding with the U-235 nucleus. To compensate for the high rate of escaping neutrons and the lower collision probability, engineers must artificially pack the small core with a vastly higher density of fissile targets. Statistically guaranteeing a continuous chain reaction in this environment strictly demands the 19.75% concentration of HALEU. The engineering that makes a reactor small and efficient transfers the mathematical burden directly onto the fuel cycle. The core can only shrink if the enrichment level scales up. Separating these isotopes is uniquely difficult because you cannot use chemistry to do it. U-235 and U-238 possess flawlessly identical electron configurations. Any chemical reaction applied to the material will affect both isotopes equally. Separation must rely strictly on the physical mass difference between the two bare nuclei, which is a variance of only 1.26%. To manipulate this microscopic difference using fluid dynamics, the solid uranium metal must be chemically converted into a gas. The industry relies exclusively on uranium hexafluoride, or US6. It is highly corrosive, reacts violently with ambient moisture to produce toxic hydrofluoric acid, and demands highly controlled industrial architecture to handle safely, but it possesses the exact thermodynamic properties the process requires. UF6 sublimates, meaning it transitions directly from a solid to a gas at a highly manageable 56.5 degrees Celsius. However, enrichment facilities draw the UF6 through the system under a deep vacuum. This optimizes the gas thermodynamics and prevents the material from solidifying inside and destroying the delicate high-speed machinery. The critical advantage of UF6 is that fluorine has only one stable, naturally occurring isotope, fluorine-19. Because every fluorine atom bonded to the uranium core is exactly the same mass, any variance in the total molecular weight of a UF6 molecule is guaranteed to be driven exclusively by the uranium isotope at its center.
But solving the phase state problem creates a new mathematical hurdle. Adding 6 heavy fluorine atoms dilutes the relative mass difference between the two molecules. The molecule containing U-235 weighs 349 atomic mass units, while the U-238 molecule weighs 352. The operable mass difference between them shrinks to a microscopic 0.85%. UF6 is the only molecule in existence that allows engineers to translate a sub-percent nuclear mass variance into a solvable fluid dynamic sorting problem. To exploit that 0.85% margin on an industrial scale, the global enrichment market relies almost entirely on the modern gas centrifuge. A centrifuge consists of a thin-walled cylindrical rotor constructed from high-strength carbon fiber, suspended vertically inside a stationary vacuum casing. The rotor spins at extreme tangential velocities, frequently exceeding 500 meters per second, or Mach 1.5. This velocity generates continuous centripetal acceleration inside the cylinder, exceeding 1 million times the force of Earth's gravity. These extreme forces create a profound radial pressure gradient. The 1 million G acceleration physically drives the slightly heavier U-238 molecules outward, compressing them tightly against the rotor's inner wall. This leaves a marginally higher concentration of the lighter U-235 molecules suspended near the central axis. This immense mechanical violence is generated solely to maintain a microscopic sorting gradient across a few inches of empty vacuum space. The radial separation achieved in a single horizontal plane is highly efficient, but on its own it is too slight to be commercially viable. To multiply this separation factor, engineers rely on an aerodynamic mechanism known as the thermal countercurrent. By artificially establishing a temperature gradient, heating the bottom end cap of the casing and cooling the top, they induce a vertical circulation pattern within the supersonic gas. The heavy gas on the outer wall flows downward, while the lighter gas near the center flows upward. This vertical loop acts as an internal multiplier. The heavier gas flowing down the outer wall is continuously stripped of its lighter isotopes by the upward flowing gas. The enriched U-235 stream is pushed to the top of the centrifuge and extracted by a stationary product scoop, while the depleted tails are collected at the bottom. Balancing this delicate thermodynamic loop inside a supersonic high-stress rotor makes gas centrifugation one of the most sophisticated industrial processes in the world. The nuclear industry quantifies the immense mechanical effort required to sort these gaseous molecules using a metric called separative work units, or SW. This graph charts the thermodynamic value of uranium isotopes. A 50-50 mixture represents maximum disorder, requiring zero separative work. But extracting pure isotopes from a natural feed of 0.7% U-235 requires imposing order on the system, demanding an exponential expenditure of work. Reaching the 5% LEU mark required by traditional reactors demands a significant baseline of SW, but pushing that assay up to the 19.75% HALEU threshold requires climbing the steepest portion of this curve. Producing HALEU requires a distinct scale of industrial effort and investment. The unyielding mathematics of the value function dictate that the resources required to reach these concentrations far exceed those of conventional fuel cycles. Because a single centrifuge provides only a fractional separation factor, machines are piped together in massive networks. These are known as tapered cascades. To reach 19.75%, gas passes through sequential stages. As U-238 is rejected downward, the volume of forward-flowing gas decreases exponentially. The cascade tapers, requiring fewer centrifuges per stage, narrowing the flow of highly enriched gas at the top. Reaching the top of this pyramid triggers a severe regulatory shift. Under Nuclear Regulatory Commission frameworks, crossing the 10% enrichment threshold instantly escalates a plant to a Category 2 facility. Because 19.75% HALEU rests perilously close to the definition of highly enriched uranium, this designation mandates armed guards, hardened cybersecurity protocols, and dynamic material accounting. The international safeguards require dramatically higher inspection efforts because the material becomes a highly attractive target for diversion. Producing HALEU requires both the mastery of advanced physics and the construction of entirely new, highly fortified industrial ecosystems. Recognizing the existential risk of relying on a Russian monopoly for this material, the U.S. government is actively deploying billions in direct appropriations to subsidize offtake contracts, permanently decoupling the American nuclear grid from foreign supply chains. The vanguard of this domestic effort is the American centrifuge plant in Piketon, Ohio. Operated by Centrus Energy, the facility houses the first new domestic cascades licensed for HALEU, reporting its first production milestones in 2023. But the scale of the challenge remains immense. The domestic supply chain must rapidly evolve from producing kilograms in pilot cascades today to outputting hundreds of metric tons annually to meet the SMR deployment deadlines projected for the mid-2030s. The transition to advanced nuclear energy depends on an extremely narrow physics margin. Delivering the carbon-free grid of the future relies entirely on scaling the precise invisible fluid dynamics of the gas centrifuge.